I'm gonna give it like one more minute because there are a lot of people that are pre-registered, so I don't know if they're just late or attending remotely. No, it's, for the most part, I'm going to do lectures on the chalkboard. Sometimes, if I'm doing a coding example, I'll pull up the projector, but for the most part, I'm not making slides. It'll be mostly chalkboard, and I'll kind of explain my reasoning for that in a sec. One more minute. All right, I guess I'm 2 minutes over the MIT start, so I'll just get started. Thank you everyone for coming. In case you're wondering and you're not sure where you are, this is the IAP course on Introduction to Applied Convex Optimization. So a little bit about the idea behind this course. MIT offers a lot of courses on optimization, but the emphasis on this one in particular is on, given a problem formulation, how do you come to a formulation that your computer is actually going to solve in a reasonable amount of time? So optimization in general is a very hard problem. The purpose of convex optimization is that this is a class of problems that we know can be solved pretty quickly on a reasonable computer. But it also sounds very restrictive. And the point of this class is to show you that convexity is not as much of a restriction as you think, and how you apply this general tool. So just a few logistics. I'm Alex Amis. There will be another lecture for the middle 3 lecturers. Benoit Legat, he's a postdoc with Pablo Perillo. So I'll be giving the first 3 lectures, and the last 2, he'll be giving the middle 3 lectures. For those of you who are going to be watching this remotely, so my hope was to give this fully in person. Obviously, the COVID situation has changed a little bit. So in order to encourage in-person attendance, and in order to be sure that people who are remote are watching the lectures, part of the grading for this class, which is pass-fail, in case you don't know, is attendance. So you get a full point of attendance if you come to the lecture in person, and you get 3/4 of a point of attendance if you do the lecture remotely. The way that we'll do remote attendance is at some random point in the lecture, I'm going to put a survey code up on the board, and I'll probably erase it 10 minutes later, and you'll have to submit that survey code if you are remote. If you're in person, there's a attendance sheet passing around that we'll just use to give you the full point of attendance. As for grading, you need 16 points to pass out of 22. A minimum of 4 points of attendance, a minimum of 2 points on final project. Problem sets are going to be very coarsely graded, 4, 3, 2, 1. Basically, there will be a handful of problems. If you do most of them and they look correct, I'll give you a 4. If you don't do any of it, I'll give you a 0, some range in between. The projects will be, hopefully, I'll give some examples by this weekend, but the idea is for you to take an area you're interested in, come up with a problem, write down a convex formulation, solve it on a computer. It'll be a little straightforward. I'll be more specific on that as I come up with the projects by this weekend. Are there any questions? So if you don't know, there's a course website. The link is actually on the course description on the IAP website. Lectures will either be posted on that website, or I'll put a link to a YouTube channel where you can watch them after the fact. I haven't figured that out. I need to see what I can do given the lecture recording that I have right now. And I did promise someone that I would explain why I'm doing mostly chalkboard talks. The reason for that is most of this class is about formulating the problem and solving the problem. There will be some discussion about how you use software to do so, but the reason to use the chalk is that people follow along in real time. If I just put up the final solution, people are going to read the final solution and be like, oh, that makes sense, and then you don't come to understand how we came to that solution. So that's why the chalk. Lectures typically will be, I'm hoping to motivate every single lecture by a case study of why do we care about this class of problems, what can we solve with it. Theory is going to be pretty limited to what you need to know to be able to use the tools in the class, and it's really going to be applied. And I do want you guys to be very interactive and ask questions. Sound good? So today we're going to talk about probably the simplest class of optimization problems that we can solve quickly using iterative methods, and that's linear programs. So to give you an example of the kinds of problems that I care about showing, we're going to start by talking about the shortest path in a graph. So we've got some graph. So most people, when they see a graph, they think discrete problem. And there are, I think everyone knows, very good discrete algorithms, breadth first search, depth first search, that searches iteratively and recursively through this graph to find the shortest path through it. I think what's surprising about this problem is that if we just write this down very naively, or very mathematically, systematically, we can actually translate this problem into a linear program, or rather a mixed integer program. And we'll see how we can actually use this kind of naive formulation to come to a linear program, which computers can solve very, very, very quickly. Okay, so let's start by, so our graph is a set of vertices and a set of edges. And let's start by saying, okay, in our solution, so the very first thing that we're going to do is we're going to introduce this variable xij. Xij is going to be binary. It's either going to be 1 if we use it in the graph, if we use it in our walk, and 0 otherwise. So if I were to walk along this edge, that's not yellow. So if I were to use those three edges, I would have that x12 is 1, x25 is 1, and x56 is 1. And I'm going to use S is going to be the start, and I'll just use T to be the end. And in this case, I'm walking from 1 to 6. Every other edge is going to be 0. So my walk is purely encoded by these binary variables. So what we're going to do is we're going to say that we're going to talk about, think about flows in the graph. So basically, if I enter a node, I want that node to have a flow. So when I'm entering a node, I'll do it this way. So let's say I'm starting at 1, and I'm going to put a unit of flow here. I'm going to think about opening pipes between the graph nodes so that I get a walk. So if I have a unit of flow here, I want 1 unit of flow to leave 1, because that means I'm going through exactly 1 edge. At the end, 6, I want 1 unit of flow to enter. So let's encode that with this. So at start, want +1 units of flow, and we want -1 units of flow. How much flow do we want at every intermediate node? 0 net. So others, we want 0 net. Why? Because it goes in and goes out. Good. So also, if you ask a question and I don't repeat it, please raise your hand again and remind me to repeat the question for the people on Zoom because they cannot hear me. OK. So how do we encode the flow at a node? So I introduced this variable xij. If xij is 1, that means I'm using that edge or flowing through that edge. If it's 0, then I don't do anything with that, right? So what is the flow out of node 1? Exactly. So basically, the flow at a node is going to be xij minus xji, right? So in a solution to this problem, what do I need to be true? Is equal to 0 for which nodes? Sorry, can you repeat that? OK, so I'm going to make this else. What should this sum be equal to when I'm at the start? 1. Okay. So this is an equality constraint on the variables in my problem. What's the cost of my problem? If the weight of the edge, so we'll call the edge weight Cij, what's the cost of the solution of my problem? Remember that Xij is either 1 or 0 here. So I want the shortest path, so I want to minimize Cij, which I can just write as C transpose X. Okay? And then I do have constraints on this problem, so I want to minimize that subject to, so Xij minus Xji is equal to 1 minus 1, 0. And the last thing I want, and then so I said this, right? So if you've already seen a linear program, linear programs come in kind of there are two standard forms depending on who you ask. So linear programs are almost always written in the standard form So that's standard form number 1. Some people will write the standard form as with an equal to instead of a less than or equal to. Those, it's not too big of a deal. And I'll explain. You can always convert between these two standard forms, and any linear program can be written in one of these standard forms. For the purposes of this class, this is one of those points where I'm going to say a fact like that, and I'm just going to gloss over it. The reason for that is almost every linear program solver, you can write much more general-looking inequalities, and your software will transform it into some standard form for you. We'll talk a little bit about the anatomy of these convex optimization softwares on Thursday. But for now, basically, a linear program is anything that you can write a linear objective and a set of linear constraints. So though this is the standard form, I want you to think of this as a linear program is anything I can write like this. Is anything I can write a linear objective, linear inequalities, and linear equalities. So, is this a linear program? I see shaking heads. What's wrong? So what's wrong is this, right? The thing I didn't say, the thing that's very important, that's different between this and this, is that I've added a constraint on the xij's that is not linear. That is not one of those 3 conditions. So a pretty natural thing to do is, so this belongs to the class of integer programs because my variables have to be integers. So usually what you do at this point is say, this is a discrete problem. It's an integer program, so it's going to be NP hard to solve. And you hope your problem instance is small enough. What you'll do in practice a lot of times, and this is what a lot of integer program solvers end up doing, is I relax this binary constraint to be between 0 and 1. Now is this a linear program? So the answer is yes. So I've made my problem easier to solve, right? So what does that mean about the objective value that I'm going to get typically? If my program is easier to solve, is the final result of the objective here going to be bigger or smaller in general if I relax the problem? Smaller. Smaller or equal to, yes. So that means this is easier to, so when it's easier to solve, your objective value is going to go in the good direction, or it's going to give you a lower bound on the solution. So what you always want to check when you relax a problem is, am I going to get lucky? So in this case, in the shortest graph problem, we can actually show that the solution to this problem, assuming a unique path, and we'll talk about that in a second, but assuming a unique path, the solution to this problem has to be integer. So why is that? So I'm going to leave that as an exercise to think about, but it's really not so hard to see, because if I can, it's actually easier to see in the other formulation I'm going to show you guys. So I'll leave it to there. So this graph search problem belongs broadly to this keyword class of problems called max flow min cut. And the reason for that is there's another way to think about this problem. Leave the graph. Can I erase this board? So there is also another way to think about this problem. Let's start by thinking about distances between the nodes. So we'll start by thinking of let dv be the distance from S, the starting node, to node V along the chosen path. So in that yellow path that I've highlighted, and I'm definitely out of the camera, so give me a sec. In that yellow path that I've highlighted, the distance of 1 from 5 is 8. So what is the distance of the start from the start? It's just 0, right? And in any given path, let's say for some node v, right, its distance to the start is always going to be less than the distance of another node and its adjacent edge. Does that make sense? I can't be farther away from the start than the edge between my neighbor and my actual distance from it. Okay. So for what is the cost of the path that I'm taking? Yep. WV is the edge weight between U and V. So this is another equivalent formulation of the exact same problem. It's a linear program, and we're solving what originally looked like a discrete problem. And this one, I don't even have to relax. For those of you who know or care, this program right here is actually the dual of this program up here. We'll talk about duality in the 4th lecture, I think. But for now, you can just think about this is 2 different ways of thinking about the same problem, and both can be solved by linear programs. Are there any questions? So if you're here, you probably know that obviously writing down these problems on Blackboard isn't what we want to be able to do. We want to be able to actually solve them. And so the nice thing about linear and more generally convex programs is that we have very strong algorithms for solving these constrained optimization problems. So in the case of linear programs, there are 2 major algorithms that you should know the names of. The first one is the simplex method. this is probably the most famous linear program algorithm. It also only works for linear programs. So I'm not going to go over the simplex method. If you want to go over the simplex method, 6255 or 6251, I think. The optimization courses go over it. The kind of broad points that you should know about how the simplex algorithm works is it starts from an easy to find initial solution. So what the simplex algorithm does, and I guess this is a good time to talk about the geometry of linear programs, so I'm actually going to cut off and talk a little bit about this. So for a linear program, what these linear inequalities actually look like, in obviously higher dimensions, is we have a set of lines in space. And what these inequalities do is they define some set which I can be on the inside of. What the equality does is it also defines a line that I can actually be on. So these are all of the, if I have some linear equality that's not over-constrained, then this is the set of solutions I'm allowed to be on. And what the linear cost does is it defines this vector field that's pushing me in some direction. So let's say I'm trying to maximize this function. I'm trying to move along this vector until I can't anymore. So if I don't have an equality constraint, if I didn't have this equality constraint, this program is, I'm just going to try to walk as close as I can up to this point. And so what these sets are generally called are polyhedra. And so there are these kind of pointy sets and what linear programs will do is generally walk along the vector field until I can't move anymore. So obviously, if I have a set that looks like this, and the set's not closed, and my cost is pushing me in this direction, I'm going to have an unbounded program. If I flip the cost, then I'm not going to have an unbounded program. So just because the polyhedra is unbounded doesn't mean that the cost of your linear program is unbounded. But if the set is closed, then obviously you will have a closed solution. So where do the solutions of a linear program, based on this picture, actually end up? Close. Yes, in most cases. So the most general solution that you can say is I will end up on the boundary of the set. Now, usually you'll end up at a vertex. So again, I'm not going to prove that. It's not so hard to prove, but I'm more interested in building intuition than anything. So so generally you'll keep walking until you hit a vertex. This isn't actually yellow. So in this picture, right, I'm going to walk here, I'm going to hit this boundary, and I'm going to keep getting pushed until I can get further and further and hit a corner, and then I can't go anywhere. The reason I say that's close and usually the case is, what if my vector field looks like that? I'm going to walk in, if I'm doing a walk through the middle of the set, and that's what one of these algorithms does, then I'm going to walk until I hit this, and then I can't go anywhere, so I'm actually not at a corner. What does happen in this case, though, is, let's pretend that my set looks like that. Any solution along this set, in that set, is equally valid, right? So what that means is I can actually take any combination of these corners, and it'll be any convex combination of these corners. And that's also going to be a solution to the program. We'll talk about what I mean by convex combination in some other time, or I guess Thursday. But basically, I can walk along this line and anything's going to be equally valid. The way that shows up in this problem right here. So remember I said that if the path is unique in the graph, then this will have an integral solution. If the path isn't unique, then you can actually end up with fractional solutions in this problem. The reason that's not a big deal is if that happens, I can just walk along until I hit the next corner. OK, so after that side note, because I got ahead of myself, so how does the simplex method start? What the simplex method does is we start by finding, this is roughly how it works again. I try to find an initial solution to the problem. That first step, if it can't find a solution, is guaranteed to say the problem's infeasible. So how can a problem be infeasible? If I turn this arrow around in this problem, then I have that this is a completely empty set, right? So if the set's empty, can't have a solution, obviously. So that first step's going to tell you whether the program's even feasible to begin with or not. If it is, what the simplex method basically does is it starts at one of these corners. From there, it's going to pivot. There's a set of pivoting rules that finds the next corner. And it asks, is this cost going to be less or more? In this case, it's going to, if I'm trying to go along this direction, and this is the direction of minimizing the cost, this cost is going to be more. So this is still my solution. Go to the next corner. Less or more? It's going to be less. So this is going to be my current status. Then I'm going to, well, I came from there, but there's another corner. I'm going to check that corner. And if this is more and this is more, then I'm done. So to do this process is going to require you to solve some linear equation like this a bunch of times. F of y is equal to g. solving this problem is usually most efficiently done using some numerical linear algebra called the LU factorization. And so solving this linear equation is kind of going to be the hardest thing that these algorithms do. And so it's very, very influenced by the sparsity pattern that this equality constraint is going to have, which is this LU factorization can typically exploit. These equality constraints are defined almost purely by how you write down the problem. And so that's, if you're trying to solve a linear program and it's taking a long time, then this is the kind of stuff that you actually want to look into. So the performance of the simplex algorithm is most heavily influenced by, if you had to guess, does it matter more the number of variables I have or the number of constraints that I have?
Constraints, because like each constraint is part of a boundary and has a lot more than.
Exactly. So it's that's the right intuition. So it's most heavily influenced by the number of constraints. Mathematically and practically, the reason that happens is because how the constraints appear in the problem affects the sparsity pattern of this f of x. So if I have a bunch of constraints that involve every single variable, this f is going to be super, super dense. The reason I'm calling this f, by the way, and not these a, l's, a, g, a, e, is because this is going to be the matrix that shows up in the standard form of your actual problem. And the reason that there are two standard forms for linear programs basically boils down to the simplex method standard form that people like to think about is the equality constrained version of that up there. And the interior point method is usually the inequality constrained version of that. The biggest advantage of using the simplex method for linear programs is that it's very easy to warm start. What I mean by that is if you have a pretty good guess about what the optimal solution to your program is, and you know that that's a feasible solution, you can more or less tell the simplex solver, start here. And if I'm close to the best vertex or the best face, then I'm going to get there much faster. So the disadvantage is that this algorithm is technically exponential time. So there are a bunch of variants of the simplex algorithm that more or less one of the ways that the solvers become more performant and things like that is they have very good heuristics on how to choose this pivoting rule, which vertices to check in what order. So technically, the simplex algorithm is exponential time. For any variant of it, you can more or less find an instance of a linear program that will take it exponentially long. It basically has to walk to all the vertices in the problem. The reason I say technically is because there's this proof based off of smoothed analysis that says you have to work pretty hard to find exponential versions, problems that take exponentially long with the simplex algorithm. So the other, I would say, main algorithm, oop. So the other main algorithm that people use is called the interior point algorithm. This algorithm is a little bit more general in that you can use it to solve general convex problems. This is probably the most common, one of the more common ways that people actually solve these problems algorithmically. So the way that this procedure works is more the intuition that I think a lot of people who are coming from this world where machine learning is very common and gradient descent and things like that is I'm going to start somewhere in my set and I'm going to walk along the gradient. I'm going to take these steps along the gradient until I hit the edge, in which case, until I hit some edge. I'm going to do this so that it's clear I'm going to the corner. But when I hit an edge, I might not be at the optimal. So I'm going to take this little step and project back. Step and project back to the corner, and so on. So the interior point algorithm, there are a bunch of variants of this one. There's log barriers. There's a bunch of ways to do this. So there are variants such as the log barrier, which I never actually exit this set. There are some where I do this walk and project, walk and project, walk and project. There's Newton's algorithm, gradient descent. There's a bunch of ways to do this. The basic idea here is that I'm walking along the inside of my feasible set and never leaving. So if you do the variant of this algorithm where I'm starting from some initial guess, I walk along the direction of steepest descent. If this is my equality constraint, and I have to project back, or if I try to leave the set and I have to project back every time. So what happens is, I'll have iterates that kind of look like this. This right here, I'm going to make this F rather. So this is only really true for the kind of projection version of it, but a bunch of these algorithms, if you look into them, will have kind of these performance areas. And so for the projection version of this, the most expensive step is actually computing that projection, which involves basically computing this matrix, this inverse right here, which will be basically solving some linear equation. And again, this is proportional to, this matters a lot based off of the sparsity pattern and things like that. But this LU factorization is, again, probably going to be the bottleneck. Go ahead.
Does that change on each iteration?
Yes. In this variant, yes. In that variant, no. I probably shouldn't use this letter. I'm going to change the G. So I don't have the algorithms written down offhand, but what'll happen basically in these variants, in these interior point methods, is you'll have to solve this problem a bunch of times to do that actual projection. And that will change based off the problem you have, et cetera.
I was wondering, sorry, would you need the step size, or is it generalized without step size?
Yeah, so the question was, do you need to pick a step size in these algorithms? Most convex optimization solvers will pick the step size for you automatically in some way. So one of the ways you can do that, or one of the ways you do that is, a lot of times, is you just line search. So you take a step in the right direction. Pretend this equality constraint isn't here. You take a step in the right direction, and you take the biggest step that keeps you inside the set. And then you can project back. Interior point methods, some of them, so this projection version takes these kind of zigzaggy steps. Some interior point methods will take these kind of curved paths through space. The log barrier tends to do that. It's called the central path. And it takes kind of the best step along some modification of your problem that you keep relaxing. Again, I'm not trying to get too much into these algorithms. I'm trying to let you guys know roughly where kind of the biggest performance bottleneck is going to be. So the simplex algorithm works really well for a lot of cases, especially if you have very, very sparse constraints. With the interior point algorithm, again, caveat, there are like 100 interior point algorithms, but those will tend to, you'll have to solve these kind of, if you're using one that solves kind of these projected steps, this is most heavily influenced by, so this G matrix and the algorithm I have in mind is constrained by number of variables. So again, if I have very few constraints compared to the number of variables, the hard part of this projection is actually going to be pretty small because it's only going to be the number of constraints I have. So this algorithm can sometimes outperform simplex when I have relatively few constraints compared to the number of variables. Because even if this matrix is pretty dense, it'll be way smaller than the matrix that shows up there. Nope. So linear programs we can solve with, I mean, some people solve them with millions of variables. Excuse me. But we basically hand-waved our way to saying that the number of constraints that you write down matters a lot. So let's take an example. Let's say I'm trying to solve this problem. Minimize C transpose X subject to the one norm of X is less than or equal to 1. Okay, and by the one norm of X, what I mean is that X1 is equal to the sum of the absolute values of my vector X. Okay, so this is not in that form, right? So if X is one-dimensional, how do I write this constraint? What's a way to write down that constraint linearly? If X is one-dimensional. Yes, so what I want is X1 is less than 1, minus X1 is less than or equal to 1. Does that work? Okay, in 2D, what happens? What do I need to do? So I need x1 plus x2 is less than 1. x1 minus x2 is less than 1. Minus x1 plus x2 is less than 1. So now I have 4 constraints. How many constraints am I going to have in 3D? Right? I'm going to need to have every sign of the xi's, every sum combination of signs of xi's is less than 1. How many constraints is that in n dimensions? 2 to the power of 2?
Oh, 2 to the power of 2.
Yeah. So okay. 1 norm constraints are kind of common. 2 to the n constraints, that's a lot of constraints very quickly. And what do we say about the performance of these algorithms? A lot of dense constraints is very, very bad. So this is an example of kind of a practical problem that can show up when you just write down things naively or try not to think about it. When you're transcribing problems, this is what you should do. Just write down the problem the way it comes to you naturally. This, though, is not a very good way of writing down this constraint. So can we do something else? Or something better to write down this 1 norm constraint? The answer is yes. So what if I write down, let's consider the ith element. The ith element, well, it's going to be some value. So I'm going to introduce this other variable, yi. Okay? So xi needs to be between the positive version of this variable and the negative version of this variable. Okay, how many constraints is this? So this is n, and this is n, so this is 2n. Good. Okay. Is this set of constraints equivalent to that set of constraints? No. Good. Okay. So what do I need for them to actually be equivalent? I need for their sum to add up to 1. Right? Because if I add up all of my constraints, then I get that this sum is between -1 and 1, which is exactly what I want. So what have we done? For the exact same constraint, I wanted a 1 norm constraint, and I wanted to be able, I wanted to be able to write it down. That took me 2 to the n constraints to write down. But that's bad. You thinking about the problem a little bit and working through this, you can actually find a way to write it down with 2n constraints, or 2n plus 1 constraints. Some solvers, I mean, for example, like the one norm. The one norm is a very common constraint. It'll do that for you automatically. However, just when you're transcribing problems in general, if I didn't have a one norm function in whatever optimization solver I'm using, well, it's not going to do that automatically for me. And so if I try to use that formulation, solver's going to be real slow. Just writing down the problem is going to take forever. If I write it down this way, way faster, going to work way better.
I was wondering if it needs the absolute value. Like in this case, I feel like defining it in the second way, you had a really large negative number that could counterbalance the larger positive value that would allow it to, in the magnitude greater than 1 for lack of number.
You're saying if I let this be super big,
Or, yeah, well, just because the sum of y sub I is equal to 1 rather than absolute value of 31 and absolute value of 0, the magnitude of the variable.
yeah, so what you have here, so this works because what I'm doing is I'm introducing a variable into the optimization problem with no cost. Well, so I'm minimizing y, but it's not entering my cost. Sorry, can you repeat your question?
I guess it was like y, so in this case, let's say you, oh wait, y sub I greater than 0, never mind, I sub I.
Yeah, y has to be more than 0, yes. You do need to include that constraint. So, yeah, go ahead.
But the way I at least zero is already implied from the first one. Because minus yi is at most higher.
Yeah, that's true. Yeah, because this is really the, yeah. So someone pointed out that there's 2n constraints already. This, I guess, technically isn't needed. You're right. Good call. So from a practical perspective, if things are taking forever, make sure that you've written down your constraints in a way that isn't making your life harder than it needs to be. Okay. So I have about 20 minutes left. The other kind of case study that I have is another kind of graph problem based off of air traffic optimization. I think I can cover some of it. This is again about just kind of practicing formulating problems. So I'm going to kind of jump into that. And with 5 minutes left, I'm going to briefly talk about 2 or 3 things on the logistics I forgot to mention, which I'm going to write down. I need to remind myself to talk about those. Okay, so let's talk about port linkage. So this example comes out of a paper called An Optimization Approach to Routing Aircraft. If anyone's interested in the reference, feel free to send me an email. I'll send you the actual paper. But let's, because I cannot draw, this box is the US. This is Boston. This is Los Angeles. I am trying to, do I have the better version of this? No, I don't. Let's say, I'm an airline, and I'm not a fan of full flights. So I think most of you guys know that airlines typically operate out of hubs. So what we have is, so we have a base city of Boston. In my base city, all of my flights originate from Boston, and by the end of the day, they need to be back in Boston because that's where I have capacity to leave my planes. What's this called? My endpoint is Los Angeles. All of the flights need to go to Los Angeles or end in Los Angeles. If I get to Los Angeles, I have to turn around and come back to Boston. I also have these slip cities. So what the slip cities are so they're cities that, so I can only stop at one of them, and if I stop, I can turn around. I don't have to, but I can. The reason for slip cities is these are the cities where my fresh crews of flight attendants are, for example. So I can actually swap crews. Or I don't actually want to be able, because I'm a bad airline, I don't want to fly from Boston to LA directly. My planes don't have enough fuel, I have to stop at one of these. So this is sector 1. This is sector 2. And I also have the constraint, because of the way I've drawn the map, I only want to stop in a sector 2 times. So this is actually kind of a realistic setup. I don't know if you guys have ever been on a flight where it's like, oh, I'm going from Boston to St. Louis, but it's actually a plane that goes Boston to Atlanta, and you stay on the plane, and then you fly to St. Louis. Southwest does this a lot, I think. So let's see. So the very first thing you might wonder is, how do I even begin to transcribe this problem? Let's number our cities in increasing order. So we're going to just number our cities. And I'm going to add the rule that, to make my life easier, I can only go to a city with a higher number. Okay? DC is lower. Okay, so these are the possible routes I can take, at least going outbound. There's also a return graph that's the opposite of this. So the thing is, I also need to be able to encode the stops, right? So give me 1 second. Apparently my phone's still on. Okay, so how do we encode this problem in a graph with the stops? So all of the connections drawn. Boston. Atlanta to what? Atlanta to Chicago. You have to, actually. Yes, you're right. Atlanta to Chicago, Atlanta to St. Louis. I think that's all of them for outbound. I'm only showing the outbound graph. If you then have an inbound graph, which is the opposite.
Can Atlanta go to Seattle?
Can Atlanta? No. In this case, no. The way we've set up this problem. So the example that is actually drawn from is a case. The paper does a case study of a much bigger area of the world. It's like Australia Air's flights. So in their example, they have you have Australia, the Middle East, Asia, Europe. So these slip cities are actually really important because you can't fly, and back in that day you couldn't fly Australia to London. You had to be able to stop. I'm just using the US so that the cities are a little bit more familiar, at least to me. This is where I'm going to switch to numbers so that I don't absolutely confuse myself. So the way you encode this problem, including the number of stops, is you build up this graph where, okay, I start at Boston. Again, I'm only doing the outbound thing, but you can actually build this graph for the whole route system. So I start in Boston at time 0. So the first index, these are city and time. From Boston, at the next time step, what cities can I be in? I can be in DC. I can be in Atlanta. I can be in St. Louis, or I can be in Chicago. If I went to DC, where can I be after that? So I can be in Atlanta, St. Louis, or Chicago. If I'm in Atlanta, I can be in DC, or sorry, I can be in St. Louis or Chicago. If I'm in St. Louis, I have to go to Seattle or LA. What is it? Or I can stay where I am because there's a gap. Or I can fly to Seattle or LA. and so on and so on. Does that make sense? Basically building up this graph at every time of where I can go. Oh, I shouldn't have erased that. Let's go over here then. Okay, so I'm going to let Fij represent the average revenue flying I to J. Cij is cost I to J. Okay. I don't have very much time, so I'm just going to introduce all of the constants. And I guess I can finish this example the next time. But essentially, I have the way I set up this problem is average revenue, cost, aircraft capacity, the demand, max number of stops, number of cities. Xij are going to be these binaries I use to encode which nodes on that graph I'm actually going to go through. Yij is the number of passengers on each route. So one of the reasons I brought this problem up was an example of a graph problem. This one, relaxing the binaries, isn't just going to give me the solution. I'm not guaranteed to end up with x. If I make xijt between 0 and 1, I will not get xijt to be 1 or 0 in the final solution. So it's not always true that you can transform these discrete graph problems into linear programs. However, for a fixed assignment of the binaries, then I have a linear program. And those I can solve quickly in the variable yij. And if you have few enough combinations of these binaries, you can solve these pretty quickly and actually schedule the entire, companies do this all the time, every day to schedule their flight patterns. Unfortunately, I'm out of time for that, so I've got to talk about this list of things. I set up a Piazza page for the class. You are welcome to ask questions on there. I will try to answer as quickly as I can on average. Assignments will be graded through Gradescope. So if you go to the course website, there's a link to the Piazza page. And on that Piazza page, there is the code that you need to use to actually enter the class in Gradescope. The reason for that is Piazza actually authenticates your MIT email. That way I'm not grading just random spam. I will try to get the first homework out by tomorrow. It will be due the next Wednesday. If there are a lot more people viewing from online than are in this classroom, grading will be slow. If it's mostly this crew, then grading might actually happen relatively quickly. I will be sending out a survey on what the last 2 lectures people would like to study. Right now, the things that come to mind are semi-definite programming for one of them, and then I can either do a lecture on mixed integer programming, which would be something like this, where I would revisit this case study, or I could do sums of squares optimization, which I am biased towards, because that's what my advisor works on for the most part. And if that's the case, we'll do more dynamic systems type stuff. And that should be it, I think. Thank you guys for coming. And if you have any questions, please just come on up. Give me 1 second.